This home video footage shows what happens when a ship breaks up at sea. Metal panels are literally ripped apart. The cargo and fuel are lost. The cost to the environment is enormous. And thousands of pounds worth of ship start sinking. Ships are built from steel. It's readily available and it's strong. There's only one problem. It rusts, making it flaky, weak and dangerous. Disasters at sea can be kept to a minimum if we understand why steel goes rusty. An investigation is set up to find out if it's because of the water, the salt in the sea, or maybe even the air. A few sheets of steel first need to be cleaned. This gets rid of any dirt and grease. Each sheet is then placed in a different tank, under different conditions. The first is in contact with air, but no water. Silica gel is a drying agent. It absorbs water from the atmosphere. A piece of cling film over the top stops any more moisture getting in.
Okay, that's tank one. Don't you go on to tank number two?
Yep.
Water has a small amount of air dissolved in it. Boiling it drives the air away. So the second sheet is in water, but there's no air.
Yep. I'll put in the oil.
Why is it important to cover the water in this tank with a layer of oil? Half filling a tank with pure water and leaving it open to the air means this piece of steel is exposed to both air and water. And finally, the fourth piece of steel is in contact with air and salt water. Rust doesn't appear straight away. The tanks need to be left for several days, allowing us to find out what steel is made of and the story of its discovery. Steel is made from iron. It's a metal which has to be extracted from iron oxide. Iron oxide is found in red rock. To get pure iron, oxygen has to be removed. This discovery was made by accident over 5,000 years ago. In the Bronze Age, meteorites landing from outer space were the only source of iron. This newfound metal was much stronger than bronze. But meteorites were extremely scarce, so iron was rare. In the Middle East, furnaces of charcoal were used for extracting copper from copper ore. Heat from the furnace turns the ore into copper oxide. Charcoal takes oxygen away from the oxide and the copper metal drips to the bottom. Adding lumps of the local red rock helped to remove impurities. Little did people know that at higher temperatures, some of the red rock would change into iron, which could be hammered to make hard metal tools. The red rock was in fact iron oxide. Heating in the furnace extracted the oxygen, producing solid lumps of iron. Metal workers soon discovered how to make iron stronger. Heating in charcoal fires and quenching in water added carbon to the surface of the iron. This produced what we now call steel. But it was a hit-and-miss operation. Adding the right amount of carbon was crucial. Too much and the steel was brittle. Too little and the steel was soft. 3,000 years ago, people all over the world began to perfect the steel-making process. Nordic metalworkers were thought to be magicians because they mumbled magic spells as they worked. But they were probably just singing songs, helping them to judge the length of time the metal needed heating. The secret of hammering to help turn iron into steel reached all corners of the world. The theory was practice makes perfect. In Africa, they built furnaces where the correct balance of carbon and iron meant that steel could be made directly from iron ore. But it was difficult to get perfect steel. Today, making steel is big business. The process has been refined, ensuring the right amount of carbon is added every time. So, how did those sheets of steel get on? The steel in contact with air but no water hasn't rusted at all.
Yeah. It's really shiny this, and it's still smooth as well.
It's a bit like putting a sheet of steel in a desert where the atmosphere is very dry. It would take a long time for a car to rust in these conditions.
It don't look like it's rusted much, does it?
In tank number 2, with water but no air, the steel doesn't rust either.
Yeah, it's no rust all the way down. Yeah.
The Titanic sank over 80 years ago. When it was discovered, it wasn't as rusty as expected. This is because, at a depth of nearly 4 kilometres, there's very little air dissolved in the water. In the third tank, the sheet of steel in contact with both air and water is very rusty. It's the iron which is reacting. It reacts with oxygen in the air and water to form the orange compound we call rust. An electron microscope's view of rust shows it magnified 5,000 times. It looks like a sponge. It's these air spaces that make rust so weak and crumbly.
Oh, this one's definitely wet.
Putting salt in the water speeds up the rusting process.
Look at it, it's even rusted all the way to the top.
So no wonder ships go rusty.
Mighty ships upon the ocean suffer from severe corrosion.
Even those that stay dockside turn quickly to iron oxide. When water's salty, wind is gusty.
Things start getting truly rusty.
Not just ships, all things of steel.
Bridges, buses, a train wheel.
We can find it,
We can measure it.
we can even learn to treasure it, we can gather it, we can weigh it.
We can coat it. We can spray it.
We examine and dissect it, but the steel, we must protect it. So to keep rust out of sight,
It's a battle we must fight.
it's a race and win we must.
Beat the clock against the rust.
Our battle against rust is primarily one of slowing it down. We can do this by protecting the steel from oxygen and water. Every 2 years, ships like this one are brought into dry dock. It needs to have any rust patches removed and to be newly protected.
Morning, Mark. Morning, Tommy. How are you? Fine. Let's have a look at this dry docking then.
Yes.
I'm a bit concerned about the major corrosion areas. Certainly these sort of patch areas here. We're going to high pressure wash the whole ship first, yeah?
Yes. And if I one coat of primer, and then the finish coat.
The finish coat to the orange.
Yes.
What sort of quantity of paint do you think for this area here?
About 250 litres per coat for the top sides, and about 500 litres per coat for the underwater area.
Right, well, look, we'll certainly get that organised today, and then we can get on with the work.
The first stage is high-pressure water cleaning. This gets rid of all the barnacles, dirt and surface rust. But but some rust penetrates deep into the steel. This has to be removed by blasting. The main method of protecting the steel from oxygen and water is to paint it. First, it needs priming. Then it's time for several layers of top coat. "23,000 litres of paint later, and the Joe Ebony is finally ready to face the seas again." If steel rusts so easily, why not make ships out of a different metal? Taking a range of different objects, there's only one way to find out. Cleaning gets them back to the bare metal. There's an aluminium pan, some copper piping, a gold ring, a stainless steel teapot, and a steel bike chain. Then it's time for a dip. Four days later, and it's time to fish out the results. First, the gold ring.
Look at it. Perfect all the way around.
It hasn't changed. Gold is a very unreactive metal, but it's no alternative to steel. It's too soft and far too expensive.
There's like no on it at all.
How about the teapot? It hasn't changed either. Stainless steel looks to be a good alternative to ordinary steel. It's made by adding small amounts of chromium during the steel making process. This stops it from rusting. But stainless steel is very expensive, and there simply isn't enough chromium in the world to make ships and bridges out of it. The aluminium pan looks
It's
much
lost all
duller.
the smoothness.
The copper has started to go slightly green in places. The steel bike chain looks as rusty as expected. So, of the 5 metals, steel, copper and aluminium are the ones which have reacted. A more controlled investigation of these 3 metals has been set up in the lab. A patch of clear sticky tape is attached to monitor any change. They're placed in salt water and again inspected 4 days later. Looking at the aluminium, the area covered with tape is still shiny. It hasn't changed at all. The rest is duller. It has reacted with oxygen to form a coating of aluminium oxide. This oxide layer isn't weak and crumbly like rust. In fact, aluminium is one of the best alternatives to steel, but it's very expensive. It's only used for making objects where weight is the main consideration. Copper has also reacted with oxygen, but only slightly. The green is a form of copper oxide. Like aluminium oxide, copper oxide doesn't weaken the metal. Copper is used for water pipes and wires. but it isn't strong enough to be a replacement for steel. It's only the steel which rusts. There's still no real alternative. Steel is strong, cheap, and widely available. So, when building large structures like bridges, engineers have to take rust into consideration. This is the Humber Bridge in the north of England. It's the world's longest suspension bridge and is made out of 30,000 tons of steel. Costing over £11 million to build, it's meant to last 120 years. So making sure it doesn't rust is essential. 6 million cars cross the bridge every year. For extra strength, engineers reinforced it with a hollow steel box running the entire length of the road. Paint protects the outside from the weather, but inside the huge steel chamber, paint isn't necessary. The most important thing is to keep it dry. Dehumidifiers do this by extracting any moisture from the air. The bridge is held up by thousands of steel suspension wires. These are protected by a process called galvanizing. The steel is plated with a protective layer of zinc. The zinc reacts with oxygen and forms zinc oxide, a strong substance which adds further protection. Every few years, the bridge has to be painted. Its straightforward shape makes this easy. But daily inspection of the steel components is also necessary. Large steel bolts hold up the suspension wires at the top of the bridge. It's vital that they don't rust. As soon as there's any sign of rusting, maintenance staff replace them straight away. Daily rust prevention, combined with careful future planning, keeps the bridge safe. The road's surface needs to be kept free from ice. Salting the road would only speed up the rusting process. An alternative de-icer called urea is used instead. All these combined efforts make the Humber Bridge a rust-free zone. Unlike the steel Forth Rail Bridge in Scotland. Why has this bridge rusted so badly? What sort of things can be done to save bridges and ships from the rust blues?